parameters and to see what we can do to mitigate their effects. So, Malfi, please.
Thank you. Molto grazie. Unfortunately, I will speak English, not Italian. If you have some questions during the talk, don't hesitate to ask it. I will try to reply to your question as I can. And this talk will not be too much technical. I just want all of you to understand well the idea behind this research we have. I want, before beginning, I want to thank all of you, in fact, and specifically Professor Ortolani. And I'm really happy to have the chance to collaborate with Prof. Ortolani and with the observatory also in Asiago. So this talk is about, I guess most of you know about light pollution, but I will go as quick as possible in that section of my talk. I want to begin with the two different ways the light is interfering with the environment. And there's basically, the first one is the uplight, you know this. We call it indirect or scattered light. The light is going up, basically hitting some particles, aerosol molecules, and go down then toward the observer. And this is the component that is very important in terms of light pollution, astronomical light pollution. But recently, we identified a second one, which is the direct light pollution. And this one is interfering more with the fauna, the flora, and also with human health. We now know that there is some problem with health. So let's talk a bit more about this part of the light pollution, the indirect light pollution. And probably you have seen this picture. I saw it in a talk yesterday. But this shows very easily what happened with light pollution, the astronomical light pollution. Basically, this light is going up to the sky and go back, and then it will add up to the light coming from the star. So the left side of this light is showing what should be a pristine night sky. So you can see a lot of stars. This is the Orion constellation, but on the right side, this is exactly the same constellation, but in a moderately polluted sky. Not in a big city like our big city in Montreal. You cannot see this. Okay, it's only in small cities probably. Here you will see it, something like that. And there's still some places that are not too affected by light pollution. And we are very lucky in Canada to have one. We call it Observatoire du Mont Mégantic. Mont Mégantic is the mountain. And it's not far from my hometown, about 60 kilometers away. And maybe you heard about this because this place is the first dark sky reserve in the world. And maybe we have the chance to discuss about dark sky reserve tomorrow, to share this experience we had with Mont Mégantic. But what we have done there, to be short, is just to, first of all, we reduce the power of the lamps all over our territory. The territory is about 50 kilometers of radius. But the main intervention was in 25 kilometers of radius. And in that part, we changed all the light fixture. We reduced by at least to the half the power of the lamps, and we remove all the uplight. Okay, so this is what have been done to restore the night sky we had before in the 70s, and it is successful. Now we have some problem with the LEDs. I will discuss about this later, but now we see an increase of the light pollution year by year since the arrival of LEDs. And what we see an increase of about 10-13% per year, which is enormous. And it is forbidden to install any LEDs into the core of the reserve, which the core is 50 kilometers of diameter. So this light pollution is just coming from outside this radius. Yeah? So it's very problematic for us. and we cannot control, in fact, the installation outside this region. Okay, let's go to the second part, which is not the astronomical. I know that most of you are from the astronomical side, but I will talk also about the direct and intrusive light. This is basically the light that comes into your bedrooms, for example, during the night. You don't want it, but there's a lot of light in the cities, and this light will be able to enter the house. This is a nice picture I want to show you. This is a project I'm doing with one of my colleague, Spanish colleague, Alejandro Sanchez de Miguel. And what we are doing with this project is to use, you know, the astronauts of the International Space Station are just taking nice picture of the Earth at night, just for fun. But we had the idea to exploit this data to make science with nice pictures. And actually it's possible. It's not easy, but it's possible. And why we want to do this, basically, two reasons. The first one is that all the satellites imagery we have during the night is colorblind. This one is color, can distinguish the color. This is nice. And secondly, the resolution is better with the image from the ISS, the International Space Station. So we can, especially for the model I developed with my team, we are interested in to know what is the color of the light, because we will see later that the color is very important in increasing, in fact, the light pollution if you are more concentrated into the blue part of the spectrum. And I'll just show you a zoom of this a specific part of the city of Montreal. And you can see on the left, green spot. Can you see it? So this is a bank in Canada. And the logo of the bank is green. And then they had a very bad idea to light their building in green, but we can see it from space. Okay, let's talk about some related issues. The first one, there's many, but I will concentrate on the health part in this talk. The first one is the energy and climate change. We estimate basically that about $40 of overlight per inhabitant in the USA, and this amount of energy is just equivalent to burning 1 ton of coal per inhabitant in the USA per year. So it's a big problem. Of course, in some countries, like in Canada, we are not using coal to produce energy, but in some other countries, it's an important source of pollution, of course. We can talk about security, especially on the road. If you light more a road, in many cases, you will increase the number of accidents. And this is just because the people feel more safe, and they will drive at higher speed, and then the number of accidents will increase accordingly. There's some good impact also on human activities. In that case, it's not a bad issue. It has been shown, especially in France, this map of light pollution has been published in Sky. What was the name? I think it's Astronomy. I don't remember the magazine name, but they published it, and right after there was a spot on the French territory with a very dark place, and then the hotel were booked for many years in advance. After that, the people in France just want to see the stars, so they went to that place. And wildlife also is well known in that case. For example, you have the sea turtle that are affected by light pollution, the insects, also the migratory birds, many others, bats and everything. So most of the animals on Earth are living during the night, so having artificial light at night can be a problem for them. And of course, astronomy, you know about this. Well, the main reason in astronomy is just, as I said before, you send light into the sky, this light is going down, and then you look to the sky, you see a combination of two light. The first one is the light you want to see, and the second one you don't want to see it. So it will decrease the contrast of the observation. And finally, well, it's not working. Yeah, okay. Let me go back. The effect on health, and we show. Actually, I'm working with some people in Barcelona, and that topic. What we want to verify now is what is the real impact of, for example, of the light at night, with some case of breast cancers, prostate cancers, and some others. So there are some studies that show that there's a link, but now we try to use my model combined with epidemiological data in Spain and try to see if there's a tight link between the two data. And there's other impact on left that now is quite well known. For example, tiredness, stress, obesity, and many other. Okay, let's talk about color. You see on the first plot that this is the behavior of the atmosphere with the wavelength, the scattering efficiency of the atmosphere with the wavelength. So most of you are physicists, I think, so you know well this phenomenon. And basically what it says is that the scattering will be more efficient into the blue. And this is why actually the sky is blue during daytime, during nighttime also, in fact. But when we have moonlight. So there's two ways to analyze this phenomenon for light pollution. If you are near a city, the sky will be brighter. But if you are far from a city, really far, then the attenuation of the light will be larger, and then the blue color will not be a problem. So it depends. It's very sensitive with the distance between you and the light. And the other phenomenon I want to show you is the melatonin suppression curve, which is the blue curve there. And this is basically the sensitivity of the human body to your internal clock, or your day and night cycle. And what this curve says that about the deep blue in more or less 460, 70 nanometers, you have a peak. And this, if you have light, more or less in that part of the spectrum, you will have an increased impact of the light on your day-night cycle. So what happens if we compare the two curves with some spectrum of light that we are using in our streets? And the first one I want to show you is the high pressure sodium lamps. And you can see that in that case, most of the light is in the yellow part, red part actually of the spectrum. And you can clearly see that there's no big interaction between this light and the melatonin suppression process. But if you look, it's the same with the scattering efficiency also of the atmosphere. If you look to some other device, this one is a white LED, and I saw that you have some in the city, not so much, but you have some. And you can see in that case that the situation is completely different. We see in the deep blue a big peak of light coming from the blue LED, and this light, of course, is unfortunately, in fact, it's fitting quite well with the melatonin suppression curve. So we should expect some problem with health if we change all the street light with that kind of LED. There are some LEDs that are less impacting on melatonin suppression. This is an example for 2.7 thousand Kelvin LED. And in that case, you can notice that the blue peak is reduced, so the net impact will be lower, of course. But we have something even better, and I'm promoting this in my province now. We call it the PC amber LED, and this light show almost no light in the blue, so you can use it without interfering with melatonin suppression. And the good news is it's also nice for the night sky. So there's many advantages to the LEDs. We will see it later, but in that case, we reduce the bad aspect of the LEDs. We just keep the good ones. Okay, so what can we do to reduce light pollution? The first one is to reduce the duration of the lighting. You just need to light when you need it, okay? Not all night long. And you can, of course, reduce the luminous flux. Most of the time we are lighting 4 times more than we need. So we can reduce easily this. We can, of course, choose better light fixtures. And by better, I mean, you know, the light just have to, for example, in a city, you want to light the street. So, but many light fixtures just they light the street, of course, but they also light all the houses around and everything. So this is not a good way to produce light in the city. So we can choose some light fixtures that are more focused on the street in that case. We can forbid uplight, of course. I see that here in Padova you have a nice light fixture on that aspect. And also the last point, no, not last point, but one of the last point is the color of the light. So you should try to use yellow color as much as possible. And finally, this is one result of our innovative result of our model. You should consider obstacles. Obstacles is a very efficient way to reduce light pollution. I will talk about it later, but basically it means that if you have a light fixture, you can plant a tree not far from it to block the light going into the house, but also going into the sky. Okay? Can be a tree, can be a building, of course, or a fence, or anything. So what we have done in my study, the last 15 years, more or less, I tried to develop two tools, and the goal is to try to understand how we should manage light to reduce as much as possible the bad effect of light. And we try to understand all of these six possible mitigations. And the first tool is, as Professor Artolani said in the introduction, the Illumina model. This model is a numerical model actually in 3D, and the goal of the model is to mimic light pollution in real environment. So we are taking into account for many things. I will list it later, but what we want to do is to reproduce on a computer as precisely as possible. There are some limits in terms of computation time, but we want to reproduce what is the shape of the environment, where are the obstacles on the environment, what kind of light you have, the spectrum, the way the light is emitting as a function of the angle, for example. We can model it with Illumina. We can also put, for example, different aerosol loading into the atmosphere, many things. The orography also can be considered. And then we are computing, I think we are the first group to do this in the world, to compute the first 2 orders of scattering. And at the beginning, it was not clear that the second order was so important, but we found that in some cases, yes, it's surprising. It can rise up to 60% of the light pollution. So it's not, before our work, most of the people were saying it's neglectable. But actually it's almost half of the total amount. And just to say, to give you some specificities of the model, we are calculating the second order of scattering, as I just said. We are calculating the terrain blocking, I mean the shadowing coming from the mountains, for example, that kind of thing. We are correcting for subgrid obstacles. By subgrid obstacles, you have to know that the model is calculating cells of about 1 by 1 kilometer. So inside this kilometer, we can indicate to the model what is the typical size and distance between obstacles. For example, if you have trees or buildings, you can say to the model, the average distance between buildings is 15 meters, for example, and you can give the height also of the buildings. And this is not an exact correction, but a first order correction to the presence of obstacles blocking the light into the pixel. We are also considering the heterogeneity of the environment. We can change pixel to pixel the ground reflectance, the elevation of the ground, the angular photometry, I mean the kind of light fixture we have can be changed in each pixel. The spectrum of the light can change also. So in the real world, you know that you can have a quite complex mix of light fixture in the 1 square kilometer. So what we are doing is to try to know inside this square kilometer what is the fraction of each kind of light fixture, and then after we can generate a fake light fixture, which is the average light fixture of that territory. Basically, this is the idea. And as I said also before, it's a pixel-based approach, so we can change everything in every pixel. The bad aspect of this model is that we need a supercomputer now to run it. So, but now we improved the speed with my students. We gain about a factor of 40 in speed, which is quite great, because before one execution need about maybe 4 days on one node of our supercomputer, and now it takes about 10 hours, something like that. So that's good. In some years, we will be able to run it on the laptop. Okay, let me show you some results of the model. This is an example. Actually, you see the big gray circles are the result from I think the first sophisticated model for light pollution, which is the Garstang model. It goes back to the 80s. But what I tried to do first is to see is my model fitting the Garstang model. In some specific case, Garstang was a model very simple, and actually it was considering cities as perfect circles with uniform luminosity. So I put in my model circles and pixel-based circles with uniform luminosity, and then no orography, for example, no mountain, nothing, and just try to reproduce the Garstang results. And you can see that it's not so bad, but there's some difference, and the difference occur on this actually the horizontal axis is the zenith angle. So if you go near to the horizon, what this plot says is that my model is overestimating the sky brightness compared to the Garstang one. And this, I try to understand what's the reason for that. And the reason is just the signal scattering. When I turn off the signal scattering calculation, the two models are the same. So it shows, just showing that the signal scattering is not neglectable at all. Also, you can see the lower curve, which is the same modeling exactly with, again, no mountains, nothing, constant luminosity, but the only change I have done is to put some trees and buildings into the model. And you can see what happened. So it's very important. Basically, a factor, in some case, a factor of 10 of the reduction of light pollution. And especially in the large reverse angles. I mean, by reverse angles, the negative one, you have a city on that side and the reverse angles are on the other side. So the sky in the opposite direction of the city will be a lot darker with obstacles. Another example of result, I have a lot, but I just want to show you two of them. And this is the release, actually the exponent of the wavelength, the dependency on the sky brightness with the wavelength, and then we try to fit an exponential curve on the results. And what we found is that basically the exponent is about 3.6. For a completely clear sky, The radius scattering is about 4. It gives you an idea. So what it says is just that the blue is very important in producing light pollution, sky brightness. This case was for a different distance from the city, and you can see that near from the city, the dependency with to the blue will be higher, and if you go farther and farther, this dependency will reduce. Actually, if you have 0, you have no spectral effect. Okay, so I think it's important, but still, if you go up to 80 kilometers, you still have a very big impact of the blue content of the light you have. So this is also an important result, especially with the LED we have now. And the second tool is what we call the in fact, we have 3 indices we developed, but I just showed you in this slide the melatonin suppression index. You see on the top MSI, this is melatonin suppression index. The second one, IPI, is for vegetation. And the third one, SLI, is a starlight index, which gives you an idea of what is the impact on the astronomical light pollution. And basically, we try to compare with this index. The index is comparing a given source. For example, we can take high pressure sodium, and we compare the fit between the spectrum and, in the case of the melatonin suppression, the melatonin suppression efficiency. And we compare this with exactly the same calculation, but for the sun. So this will give you a number without units. And this number will go to 1 if you have the sunlight. For example, the moon will give more or less 1. But if you go to bluer light, you will have also big values in the MSI. But if you go to red light, then it reduce up to for very LED. Then that 3 typical. First one on the top is and 1,000. It's about it can show about a factor the initial have with the if you for LED, then you will reduce power in light pollution. Side we have the index. A given. We can do it for other anything, but you need the curve, of course. We just understand what happened with plants. Okay, and what happened if impact of way to reduce light pollution? We make maximum one or another the more people living in the cities is control the time way to do it, except of course for the in that case of the streets it's quite efficient. in Padova, but in North America. And then reduce a lot light pollution in the houses. So then you can work on the color of the light to reduce the light pollution by a factor of. In that case, I check for the cobra. Maybe you. Like it's this kind of light will emit about. It by light, which emits 1% to. Yeah, for us, in the house, it will change nothing. But if we look to you can see that the impact will be changed, and the other again, time is the best. Shut down. So I remind you that in the living, it's very efficient, about 5 times light pollution by taking to me that the light intensity change, but increase the number of light fixtures. Okay. Quite efficient, about 5. Compared to HPS. And in many places the intensity by a factor of the administration were nobody noticed it. It's very nice for astronomers. Efficient way. This is efficient to reduce just the concept of light, which is better with LED. Actually, they are less efficient than if you have a good sodium lamp, and you can gain this 40% of. It's just that because the new light are more. Use some examples of transformation we have made in Sherbrooke City. just walking in the park, seeing nothing because they had the outside the surface you want to light. And the grass, we help the grass to grow, but it's not very useful. And what we have changed, in fact, is just to change the optical system in the light. And you can see that after we are not lighting at all the grass, or more, very lowly at least. And we also reduce a lot the glare for the people. And if we use the table I showed you before, inside the city, okay, you have two factors. The first one is 1. It means cutoff plus well focused. This is 1 because we are looking to the light entering the house, and it's not doing so much for that, because the light will go anyway, will go into the city with this. And so this is why I've put 1, but actually it can be a little bit more than that. And the 1.4, excuse me. And after we reduce the light intensity by a factor of 4, which reduced by a factor of 4, it's really the light pollution. And at the end, the net result is 18% of what we had before, which is quite good, and it costs a very low amount to the university. Actually, they save money because we cut the power consumption by a factor of 4. And another example is in the second university in Sherbrooke, which is a small university. And this is a Bishop University. And in that campus, what have been done some years ago, unfortunately, there's an observatory on the campus, but somebody decided to change the sodium lamps for white LEDs. And then the physics department was very disappointed with this because it was completely impossible to do astronomy after that. And we succeed in convincing first the university administration, and secondly the company who sold the white LEDs to change the white for amber. And finally it was possible. It cost some money to the university, but we agreed to do this after a while. And if we compare the two impact of each way to light the campus, you can see that just for the first number, you have two numbers, 4.1 and 2.6. This is 4.1 is the factor going to white LED to sodium lamp, and then sodium lamp to PC amber. You have a factor of 2.6. So you combine the two, it will be more or less 10, 12, something like this. And then the other way we choose to reduce light pollution, in that case, is to reduce the power to 50%. So at the end, we have 5% of the initial impact on light pollution, which is quite good. Of course, it costs something to the university, but in some years they will recover the money with the energy savings. And I want to show you a last example. This one is hypothetical example made with the model. What we want to see is what will be the impact of changing all the HPS, all the sodium lamp of Montreal City. This is Montreal City, for example, white LEDs or amber LEDs. And we have done this work using the ISS calibrated images. And what we found is that basically if you change to 4,000 K LEDs, you will increase the light pollution by a factor of 3. Okay, I have to say something to mitigate this result, because we decide to put the same visual illuminance on the ground. Actually, if you change to most of the time, when we change to LEDs, we reduce by 40%. So this is not exactly 300%. It may be more 200 if you take into account this reduction in flux. And if you change for PC amber, then it's a reduction of light pollution. It's very nice, no? You will go to about 30% of the initial health impact. If you are more interested in the effect on the night sky in the city, then it will be a bit lower, a bit more than that, not 30%, but maybe about 40%, because in that case, you know, the human eye is during night is sensitive to the blue, but not as much as the melatonin suppression. So it will have a good effect, but not as good as for the health effect. So, my conclusion. Are LED attractive for street lighting? Well, there's two answers, actually. Yes, it is, because LED are easy to control. This is a good point for them. They usually have no uplight. They are well focused on the street. This is good. They said that people from the industry say that they are long-lasting. I'm not sure of that. But maybe some of you use LEDs for their own personal use, and they found that maybe it's not true. But if we believe to the industry, it can be a nice point. But on the other hand, no. Why? Because there's a lot of blue in LEDs, most of them. And the bad news is that the blue peak of LEDs is fitting more or less the melatonin suppression and also the nighttime vision of human. They are more scattered into the atmosphere, so the impact will be more important for astronomers. And a bad thing is that when your LEDs are over, you cannot just unscrew a bulb. You have to change all the electronic system inside. So globally for the environment, it's not obvious that it's an advantage to switch to LEDs. So, but it's still okay. It's not clear, is that very interesting, but we have good news. Because we can keep the advantage of LEDs while reducing as much as possible the bad aspect. And this is possible with, as I said before, with the amber, PC amber LEDs. So you will reduce the blue problem because there will not any blue in this spectrum. And the other good news to me is that now with the results we have made with the model, you can have a table for the people from the city administration that they can use to try to mitigate the total impact on light pollution in their own city without having a big model to run. You know, this is the point. So it's quite easier for them. So that's all I do. You have some questions?
So I have many questions, but I let the people before me.
Well, one question about our perception of the net. I think it's a real problem when you are dealing with protected areas. It doesn't change that much. In fact, they have used, I guess, the Canary Islands for protected areas, or in Chile also, I guess. I saw some colleagues in Chile presenting some.
In Chile, they have some cases. Just to say some words, but they favor now the 3,000 K in Chile.
What about convincing administrators to switch to amber LED?
Yeah.
Because the problem they always present is the color perception.
Yeah. I think we must distinguish two things now. The amber LEDs, there are two kinds of amber LEDs. The first one is the monochromatic one, which is a peak in the amber color, okay? Very restricted in wavelength, about only 30 nanometers wide. And the second one, the one I showed, is the PC amber. PC amber is wider. It's covering from more or less the green to the red. So you still have a not so bad color rendering. Okay. And my other answer is that to be honest, we have to compare apple with apples. What I mean is that now we have, in many cities in the world, high pressure sodium. And compared to high pressure sodium, PC amber are a lot better in terms of color rendering. Of course, if you compare to white LED, we cannot compete with white LEDs in terms of color perception. But the question also is, do we need to differentiate colors at night? We never had this change of color perception. But the question also is, do we need to in the natural environment? Why should we have it now? I can understand in some cases, you know, for some, I don't know, maybe in the hospital entrance you need to see is that blood or oil or water. This is, to me, it's only in some specific cases that maybe you will need white color, but not on all the streets.
Scusate, una cosa operativa. Siccome noi siamo in public screening in questo momento, allora quando mi parla il microfono si sente, siccome non abbiamo microfono non si sentono le domande. Adesso ho chiesto che serve un microfono, se nulla. Ah sì. Se non avete niente contrario di parlare al microfono in modo che possa essere registrato anche l'intervento. Altre domande?
Well, again, me, at this point.
Yeah. You showed us in the beginning of your presentation an experiment, a kind of georeferencing of astronaut images from ISS.
Yeah.
Well, we did some attempts here too, and also using as a final output Google Earth file, so everybody can click on the map and enlarge it and visualize the corresponding image during daylight and during nighttime with the background of the ISS. It's, as you said, this is only pictures of beautiful places. When astronauts are captured by their attention is captured by something interesting, they take a picture.
Yeah.
And as we pointed at the Mexico City conference of UNESCO, it would be great if astronauts are more sensitive to these problems and take more systematic way, images of the same places, for example, or wider areas. We were lucky; we had a beautiful image of the entire Veneto region, almost, excluding the mountains. And that was the only one.
Yeah.
So it was a long time ago at this point. So you cannot see the differences. For example, in switching to LED light illumination.
In Milan, you probably saw the.
Yeah, that's famous. Yeah, that's famous.
It's a well-known, probably one of the only very clear you know, the before and after the change to LED.
Well, I am happy that I saw that you are in contact with this project of Globe at Night.
Yeah. No, not the Cities at
Cities
Night.
at Night, sorry. Well, it would be great if all together we try to press NASA, for example, because we tried with Italian astronauts and we didn't have a great success in convincing them. It's also hard to approach them sometimes and get close and try to, hey, Ella, you should pay attention to this problem. Yeah. So probably on a worldwide base, it would be easier to convince them. And that's what I expect in the future contacts with you and the experts of Cities at Night.
Yeah, now they are open to suggestions. But, you know, it's not officially in the program. This is like just for fun. And what we see is that most of the time, for example, if there's a Canadian astronaut in the ISS station, if we have, most of the time we'll take a picture of Montreal, Toronto, but maybe not in the cities of other countries. And there's also a selection for the well-known cities. You know, probably I did not look at it precisely, but probably there's more images from around Venezia than Padova. Just because it's a touristic place and they just want to take it in picture. But I know that the NASA now is open to suggestions. So maybe we can submit a lot of suggestions. It can be one of them can be just to favor a more systematic picture taking by the astronauts. But you know that this was not a scientific program at the beginning. Unfortunately, but we try. Having this database is so important for us. We want to use it, of course. All the I didn't mention it, but all the satellites that are at work now at night are colorblind, so they cannot see the blue. They are not just colorblind; they not see at all the blue light of the LEDs. So if you compare, and some people have done that to compare before and after with a LED conversion to white LED, and they found that the light pollution is going down, but it's not true. They just don't see. They just see a part of the light with this, and in fact, in the case of the sodium light, there's almost no blue, so it makes no difference with the satellite, but with the LEDs, it makes a big difference. I don't know if I answered to your question well, but
okay, there are two more questions.
Here you are talking to an audience that is of researchers and students or professors, but when you talk to normal people and you tell them that light pollution is dangerous for their health, for breast cancer we saw, for prostate cancer, tiredness and obesity, what are the issues, the problems to deliver, to convince them?
To convince the normal people, you mean? Oh, it's strange. I don't know. There's two. This is a good question. I'm not sure I have the answer to that. But what I notice is that many people are fear from the night, and it's very strong phenomenon. They are fear. It's not, logical behavior. They just fear. And my experience, I go to the media in Canada and I try to convince people. Now I had access to the mayor of the city of Montreal. He meet me, and so I'm proud of me for that part. But I had a lot of work to gain this. But the normal people are just thinking, again a new problem, and then they will say us that taking a breath of air is bad for their health. I don't know. They are just another pollution. My God, what's that? The light. The light is so normal. It's not pollution. For the normal people, it's not obvious to see that there's an impact on their health. But fortunately, fortunately, I'm not sure it's a good news, but we found that there's some effect, and now the medical association are beginning to say that, and it took about more or less 10 years for them to do this. But now recently, maybe you heard this in the media, the American Medical Association declared that actually white LEDs are bad for health. So this is good for us because we can, normal people don't believe, in Canada at least, they don't believe the researcher and the specialist, but they believe into the physicians. And unfortunately, it's the case in our country. Yeah, so it's good for us that if the doctors are saying the same as the doctors.
When we buy it, so warm light lamps for home are amber?
No, they are not amber. There are some in Canada. We can find some. They are sold for to mimic candle lights. But it's a new product. At least in Canada, I just myself. Of course, it's strange because I buy a lot of LEDs. I'm a bit against them, but I have a lot in my house. But you can find, you look to actually the color temperature, and depending on the period of the day you are using this light in your house, for example, in the kitchen, more or less you are using it during daytime, no, not at the end of the evening. Then you can put white light. To me, it's not a problem because it will just wake you. It's good actually. But in your, I don't know, if you just relax in a given room, the living room, for example, maybe it's better to put amber. Yes, if you find it, yes. But otherwise, maybe at 2,700K is not so bad. We found with the, the index, the melatonin suppression index, that 2,700K is more or less the same as the incandescent bulb. So it's not so bad. You can use it. But going just to 3,000, there's a substantial difference. And 4,000, forget it, it's not good.
Can you show the slide, the comparison between the Garstan model, please?
Yeah. After that. Okay.
Thank you. In your model, you consider only the mean distance between the obstacles, or also altitude, physical characteristics, if we are building trees?
Yeah, the problem is that, we are considering it. The problem is that for 1 per 1 kilometer square, you cannot have different height. Okay, so what we are doing is to look at Street View. We go with Google Street View on the given. We just estimate the height of the building. What is the height of the lamppost also? We was doing nothing. 1 kilometers from 1. We can consider it, of course.
You have a mountain?
Sure. The model, you have a given the ground reflection. We are using it. The something. The elevator. It's not so accurate.
My curiosity, a river or
the water is like a trap for the light. Of light reflection is about 3–4% only. We have using now the input is under, but previously it was of about, and it was a problem inside this 5 kilometer. Doing the computation, it was the satellite bad, and then the result was very bright. So, and now we don't have this problem with the new. Some original image to remove.
May I have a question? Okay, starting from this.
Yeah.
Quite is partially empirical.
Yeah.
Here in this picture, what is the truth? I mean, the real. Yes.
Because before publishing, for validated, and we have some. But there's a very important difficulty. But the problem are highly variables. And the night brightness, but this value is changing. It's the same in every place. So that beginning of the night, but more at the end of the night. And at the end of the night, the sky brightness is just a microclimate layer in the atmosphere. So in the model, it's not so easy to have. It's easy. Example of Canary Island. And at the beginning, at the early morning, theoretically, we know that it must, our solar relative humidity is increasing accordingly. Size with humidity, but we don't have.
Also to the issue in the end, the sky bright. So since you have the variable aurora,
done in our case is to design a spectrometer but this instrument is just taking all the spectrum. So with the spectrometer, the good point and some of them are not five spectral lines. We are sure that and this is one reason why that's it. But now we can put direct.
it's an issue which was raised by advantages in the use of a full cutoff and also to put, as you said, obstacles like trees. Trees, in fact, are dangerous inside the city. If it is windy, full cutoff lamps have the advantage they don't put light up, but the light footprint is smaller. So you need taller appliances or more frequently. And in both cases, you have a number of problems, because if you put a taller, then the light pollution can start, can increase somewhat. And if you put more, okay, there's an issue of costs. There is another one, I don't know if you said, we had long discussions about it, that when you put the flat mirror, the efficiency is lower than with the curved mirror, glass.
Glass.
Because of the reflection, because the angle of reflections. So.
Yeah, but this is a good question, because actually the choosing a real full cutoff light is like having beams. It's hard to cover a long distance with this. This is true, and to my point of view, it's not necessary to do this. Having light, not full cutoff, just you can allow a few percentage to the sky, because as I showed, it's not it's a good way to reduce it, but not the only one. And especially if you have obstacles. And here, for example, I guess it's we can generalize it to Italy. But if you look to your city here, for example, the light fixtures are always lower than the buildings, right? And the buildings are quite narrow. So in that case, we showed with my students recently that in that case, having, of course, we don't want to send all the light up, okay. But just having even 10%, maybe 5% is not a big issue, because this light will be mostly blocked by the buildings. The problem arises when you are far from the city and in the countryside without obstacles. It happens. It happens, but it's another problem. We had a recent study at Alexandre. My students will show it in a meeting soon, and we have tried an experiment for Hawaii. In the case of Hawaii, in the Maui Island, in that case, there's absolutely no obstacles. This is not true. The houses are lower than the light fixtures. So it's like having no obstacles. And what happened is that the light, in that case, switching to LEDs is not so bad. And this is why? Basically because LEDs are more or less cut-off devices. So then the reduction will be very, very high. But if you have obstacles, it makes a small difference, but not so big. So in your case, I think you don't have to focus on that with your administration in your cities, because I don't think it's important.
Thank you.
There's another voice.
What is the color rendering index for amber LED?
I'm not sure. I think it's 76, but I'm not sure. It's not bad, but I don't remember exactly. Maybe if you have internet, I can maybe look at it, but maybe later after the talk. But it's surprising. It's not too bad. Yeah. As I said, amber LEDs, real amber LEDs are really bad. It's a bit like the low pressure sodium. Yeah. It's still yellow. It's still yellow, but you are able to distinguish color, not to have the real feeling of the color, but distinguish.
Well, if nobody else, I have an ethic question about LED, particularly the red, on the red side of the spectrum. The correction is typically done by using dyes in the LED, and these are typically elements or compounds of elements which are hard to find, and they can raise up some ethic questions for the countries they get them. So this diffusion of amber LED or color-corrected LED, it can be a problem because they require a lot of. I was so impressed when Sergio showed me. That's why I started doing some literature research on the commercial LED, and he found some europium in the local spectra of the sky. So and I found that actually organocomplexes of europium are the most diffuse dye. Actually, the red pixel in the screen of our cathode TV screens are with europium. So the spreading the use of these elements can raise some particular questions. So my final question is LED the frontier of light? Is there any alternative appearing on?
I think up to now is quite difficult to find other ways.
Because for some reasons, I guess it's better to get back to sodium.
I think white LEDs is not the last thing. I think, but you were mentioning the elements to produce the light, right? Okay, because in the white LEDs we produce blue light, right? Of course, these elements are probably very difficult to find and very rare in the environment. But what we do to produce white light is to put phosphor, right? So what is the difference between white LED and amber LEDs? Just the thickness of the phosphor layer. Okay? So in the two cases you have phosphor. You have a bit more for the amber. The point is that, to my opinion, white LEDs is just a bad technology. It's we try to sell the technology before doing all the R&D, research and development on that process, because some people now are working, for example, on RGB LEDs. They are not as efficient as we want, but if we continue research on that field, it can be increased. And with that kind of light, we can just reduce, for example, at a given time, the blue component to get something like an amber light during the night. So you can modulate the color, which is impossible in fact with the white LEDs or the amber LEDs. And one question also that is not so clear is what will happen for white LEDs with time, with the phosphor. Is that a stable material, or it will be with time less efficient to convert blue to yellow? And it is not clear. We know that when there's some UV in the light, there's a degradation, quite rapid degradation of the phosphor, but with the blue, surely it's less steepy, but we will probably experience this in our street in some decades. But I guess the lamp will be out of order before, maybe.
So thank you, Martin. I think it's... Martin will be here only short time because he is going up to Asiago, I guess. So if you have something to ask him, do it just now. Okay, thank you.
Thank you.